Hi, my name is Ari Collings. I'm a fourth-year honors student in the Faculty of Computer Science. For the culmination of my degree, I decided to do my honors study on emergent control methods on the mobile web. I've been working on a web-based mobile game for the past several months, with the goal to use the device's gyroscope and accelerometer sensors for controlling the game. During my development, though, I came to realize that utilizing these sensors' data in a stable and standardized way was a lot harder than it should be. Despite nearly all mobile devices containing hardware for detecting linear acceleration and orientation, the APIs and data that they return have historically been incredibly fragmented between operating systems and browsers. Different manufacturers include different types of sensors in their devices with varying accuracies and capabilities, and atop that, each operating system interprets this data and passes it onto the browser differently, resulting in data that is very difficult to acquire and use consistently. Because of this, applications of motion control tech on the web are rarely explored, and all previous attempts at creating libraries to standardize these sensor readings that I was able to find have been abandoned. This is really unfortunate, because motion sensors have a wide range of application for creating immersive and useful experiences. They can be used to create engaging motion-controlled gameplay in mobile game projects, or used to track movement and heading for GPS-based mapping applications. They can be used to determine device orientation for AR or for 3D star map viewers, or they can even be used for exercise tracking as pedometers or fall detectors. Gyroscope and accelerometer readings are widely applicable to many different fields of software. While it's true that stable APIs for interacting with these sensors have existed for a long time for native applications on iOS and Android, the web has been accelerating and replacing traditional apps for many types of projects, on account of the reduced barriers to develop for it and to consume content made for it. The game I'm currently developing is built entirely using web technology, as it allows for one codebase to be used to create an experience on all sorts of different operating systems without having to drop down into individual OS APIs or release separate applications for each system's app store. As we look forward into the future, I believe that web-based technology is a key step into removing the walled gardens and incompatibilities between different devices, and the exposing of more low-level device features into its ecosystem is an important and necessary step. So for my part in all of this, I decided to try my hand at creating a library myself. A library which collects and standardizes both linear accelerometer and gyroscopic data from the host device, standardizes it and converts it into a platform-agnostic format, and scaffolds over the potential differences in sensor capabilities by using sensor fusion. This library was published on April 16th as Motion Observer, and this video seeks to document the research, discovery, challenges, and outcomes of its development. To start with, let's discuss the state of things before this project began. From my research on MDN, I learned that the web has two built-in APIs for reading accelerometer and gyroscope readings. The older event-based system, which implicitly starts listening to device sensors and dispatching information as soon as an event which reads sensor data is bound by JavaScript, and the newer sensor object API, which exposes a number of sensor objects which can be independently initialized and read from. The newer API is far more flexible and is the direction that browser maintainers are moving towards for exposing new sensors, such as ambient light and magnetic field readings. However, it is currently only supported in Chrome, which immediately rules it out for the purpose of creating a cross-platform sensor library. My research also led me to WebXR, which is a set of newer technologies being integrated into the web for the purpose of creating immersive AR and VR applications. During my research, I considered using its integrated spatial positioning system either as a replacement for or to complement accelerometer input for motion detection. However, it's similarly lacking in browser support, with iOS requiring an independent app to run experiences built for it, and it's also architected in a way that makes it very difficult to use in the background, as it expects to be used in tandem with a full-screen 3D visualization generated by the API itself, presumably to avoid abuse. So that left the only option being the old event-based API for accelerometer and gyroscope, which actually has pretty solid compatibility metrics, being supported on nearly every major browser since around 2015. Unfortunately, a green checkmark on a compatibility chart doesn't often paint the full picture when it comes to cross-browser APIs, and for motion sensing, it didn't even begin to cover the full extent of how varied these readings were. The documentation was riddled with asterisks, including vague descriptions about how Chrome and Firefox handled linear acceleration coordinates differently, of course with no source or elaboration about how they differed. There was also notes of an iOS-specific non-standard permission system, which was entirely undocumented on NPM, and I was also unable to find a reference for it in the Safari developer documentation. On top of that, each sensor had two different readouts, with no static way of determining which, if either, a device supported. And across it all, there was virtually no information about the spread of hardware support for each type of reading, beyond a stray note on NPM stating that the APIs themselves were quote-unquote widely supported. So after getting the lay of the land as far as the official APIs were concerned, I decided to look at pre-existing libraries which attempted to accomplish the same thing I was doing. I found a couple of libraries from close to a decade ago that seemed to do what I wanted, but everything I could find was either abandoned, used such old JavaScript that I wouldn't be comfortable including it in a modern project, or most often both. I also found evidence that Three.js, which is a popular high-level gaming development library for JavaScript, used to have a device orientation controller add-on, but after looking into it, I discovered that they scrapped it several years ago due to their inability to develop a reliable implementation that worked across all devices. Satisfied that there was no existing libraries that were both compatible and maintained, I moved on to the task of developing one myself. For my testing purposes, I collected 3 devices: an iPhone 12 running the latest version of iOS, a relatively high Android phone which is my daily driver, and a very cheap Android that was bought as a backup for an out-of-country trip earlier this year. I loaded both of the Android devices with Chrome and Firefox, which together represent both Chromium and Gecko, which nearly every browser on Android is based on, and on the iPhone I stuck to just Safari. Outside of the EU, all iOS browsers are regulated to use Safari's WebKit under the hood, so Chrome and Firefox on their platform are actually little more than skins over Safari's rendering engine. With these devices, I was satisfied that I had a large enough spread of devices to cover the range of possible API differences. I started out by building a simple demo for my high-end Android phone, which used gyroscope readings to orient a 3D camera, to confirm my understanding of the sensor readings and ensure that what I wanted to do was supported. This actually took a lot more time than I expected, as I found that the event-based device orientation readings from the browser only returned an orientation as Euler angles in local space, not as quaternions like the modern Sensors API. Ultimately though, the code required to convert them into a quaternion and then the 3D rotation matrix was trivial, but my lack of confidence with 3D mathematics definitely hindered me here, and it took longer than I would have liked. After getting my first test working, I decided to answer a question I'd put a pin in during my development. In the event-based API, there was 2 events to retrieve orientation: device orientation and device orientation absolute. According to the W3 specification for the events, the difference is that the absolute events are always relative to the Earth's coordinate system, whereas the non-absolute events have an arbitrary coordinate system left to the implementers. I decided if the library were to return information in one of these systems, the absolute one seemed simply better, as it was hypothetically guaranteed to remain consistent across multiple invocations of the app. But as the spec described the absolute events as being acquired using multiple sensors, including a magnetometer, I figured it prudent to confirm whether or not my testing devices even supported the events in the first place. I'm lucky that I did, as while my high-end phone supported the absolute events, neither the iPhone nor the low-end Android phone reported any data while listening to them. This was troublesome, as there is no way to my knowledge to query if the device supports the sensors directly. It can only be inferred by the presence of the events being issued or lack thereof. I decided that for my library, I'd consider the orientation events being in the absolute coordinate system as a progressive enhancement, indicating that they're absolute with a Boolean property returned by my code's events, but not allowing the user to directly request only absolute readouts, as they wouldn't necessarily be available. Testing on the other 2 devices confirmed that the non-absolute events at least had a standardized down direction pointing towards the Earth's core, so the only difference between absolute and non-absolute readouts was the origin of the alpha value, which was the phone's compass heading. Unfortunately, as I mentioned before, there's no way to directly query whether or not a device supported absolute orientation. The best I could do was attach listeners to both the absolute and non-absolute events and attempt to determine if absolute events were being sent before dispatching anything to whatever code was using them, as otherwise there would be a sudden jump as the coordinate system changed from non-absolute to absolute space. To determine if this was feasible, I decided to test the intervals at which the events were reported, and I was happy to see that if both events were listened on for a device that supported both, they were issued in relative lockstep. Every time a non-absolute event was issued, an absolute one was also issued at nearly the same time. Using all of the information I gathered, I developed a solution to the problem for my final implementation. When a user of my library requests device orientation information, it adds listeners to both the absolute and non-absolute events. If an absolute event is read first, it immediately discards the non-absolute listener and begins dispatching absolute events to the user. If a non-absolute event is read first, though, it starts a short 20 millisecond timer. During this time, no orientation events are dispatched to the user, which gives any absolute events which may be dispatched by the browser a chance to delete the non-absolute listener if they occur. Once the 20 milliseconds expire, the library assumes that no absolute events will be fired ever and instead deletes the absolute listener and begins issuing the non-absolute events as usual. In my testing, this method properly identified the device's capabilities every time. From there, aside from some iOS-specific compass-related properties which I passed through unaltered, I found no other device-specific inconsistencies. After that, I moved on to linear acceleration. Accelerometer readings are also delivered in an event-based architecture. Several hundred times a second, the phone dispatches an acceleration event containing an acceleration vector in the device's coordinate frame and the interval it was sampled at. Similar to orientation events, these had 2 different variants that required different hardware. An acceleration vector including the Earth's gravitational pull was provided by all the devices I tested, but there was a second property which represented the acceleration vector with the force of gravity isolated out from it, which the low-end Android phone was not able to produce on its own. Unlike orientation events, I figured it would be prudent to expose these different measures as separate events to listen on, as building a system that might receive acceleration including gravity or might not would be extremely difficult from an implementer's perspective. So to begin with, I scaffolded out 2 event types which could be listened to, one for each measurement type, and then forwarded the base JavaScript events from the browser to the listeners of my library. From there though, things got a little more complicated. Similar to my rationale for making orientation events a progressive enhancement, I didn't want to expose events from the library that only had a chance of being available. The entire point of Motion Observer was to obfuscate the differences in devices so that experiences could be developed irregardless of the underlying device and hardware. So I set out to discover how I could derive one from the other so that if a device supported either of the measurements, I could allow the user to receive both. The first step for that was to actually determine which of the formats a given browser was able to emit, similar to device orientation and device orientation absolute. Unlike those, however, the different types of data didn't come in 2 separate events. Instead, both readings were given in one event, simply called device motion. This posed a different problem for me, as instead of being able to just check if the events were being fired at all, I had to actually infer from the data that was returned if the required measurements were being performed. In the MDN spec for the event type, both properties, acceleration and acceleration including gravity, were optional, which suggested that they would be emitted if they weren't able to be measured. However, in my testing, I found that they were frustratingly still present even if they weren't measurable, and just had each component of their vectors consistently zeroed out, which was far less useful. Thankfully though, it was still relatively manageable to infer if the data was actually being recorded or just defaulted. On all the devices I tested, acceleration data was consistently fired hundreds of times a second, even when the device was at rest, with countless micro adjustments and tiny vector offsets to the measured acceleration. There was never a circumstance where a property I was actually measuring returned all zeros for any meaningful amount of time. So I ended up writing a similar framework to the orientation system, where as soon as a motion event was received, I'd capture all of the events for up to 20 milliseconds, and if no non-zero gravity-emitted acceleration was detected, I'd flag the device as incapable of measuring them. In my testing, I never got a false negative. Through this testing, I also determined that the acceleration including gravity property was never not measured in any device or browser combination I tried, meaning that I didn't need to worry about re-adding gravity to a gravity-less vector, I only had to worry about isolating the gravity out of a vector that included it. I was initially worried about how I would reliably do this, but for reasons that I'll discuss further in the limitations section, the readouts for the accelerometer were already so noisy and prone to drift that I was able to simply apply a constant 9.8 meters per second acceleration counterforce to the vector in the up direction to counteract the gravitational force, which was measured by the gyroscope. The concept of applying measurements from a sensor to compensate or improve data from another is called sensor fusion, and although this implementation of it is admittedly very primitive, it worked really well. The concept is actually really critical for collecting accurate measurements from real-world sensors, and is often used in more demanding environments and integrated systems, such as in aeroplanes and rocketry. After that, I had to address the vague claims that the coordinate systems returned by acceleration events were different across different browsers and operating systems. In my testing, which I believe represents all of the significant device/browser combinations, I actually found that they were mostly consistent, which indicates a lot of improvement since the documentation I read was updated. I did find that measurements on iOS were entirely inverted from the ones measured on Android, with the signs of the components in the vector being the exact opposite of the ones on the other OS, which suggests that they have different reference points for what part of the device is considered down. To fix this, I simply inverted the measurements on iOS to align with Android, which standardized the measurements across both devices. The final OS inconsistency worth noting was with permissions. Android allows free access to sensor readings so long as your page is served from a secure origin, but iOS requires an additional permissions dialog prompt which must be instigated by a user interaction. This is a common, if inconvenient, pattern across the web. Most permissions dialogs for privileged features will silently fail if they're not displayed in response to a user gesture. Ultimately, creating a situation where the user is prompted to allow access to the sensors is an exercise for the user, so I didn't really dwell on that for this project. However, I did still want to make sure the library code was as robust as possible, which required a bit of designing to get right. I created a static function called requestPermissions, which first tests if the underlying OS even requires a permission prompt by checking if the requestPermission property is specified on the native device orientation event, and then it invokes it to give the user a permissions prompt if it does. After the user makes a decision, the promise returned by the requestPermission function resolves with a string granted or denied, which my requestPermissions function branches on to determine if it should resolve successfully or reject. Because it's a static function, it can be invoked at any time by the user, meaning that implementers are free to add it as a callback to pressing a start game or grant permissions button at their discretion. It's also automatically called by the library method, which starts listening for motion events as a second attempt to acquire the permissions if they weren't requested before. This code was a little bit messier than I would have liked on account of the iOS permissions functions not being a part of any standard spec and therefore lacking any TypeScript type definitions in the standard library, but ultimately it just took a little finicking around to get working properly. After that, all was left was to clean up the code and structure it in a way that was easy to work with. I'd been depending heavily on Three.js for its vector, quaternion, and matrix math helpers for a lot of the coordinate transformations I was performing, and I wanted to drop that dependency, as it's a very game-specific framework and it weighs in at about 600 kilobytes, which is relatively high for a web library. So I ended up digging through the Three.js source code and simplifying and adapting the required mathematics directly into my project, which ended up having a pretty small code footprint. Thankfully, Three.js is open source and licensed under MIT, which is also the license I wanted to use, so there was no conflict with doing this. For structuring the actual user-facing API, I decided to go with the observer pattern, which JavaScript has been using for recent event-driven interfaces like resize observer and intersection observer. To be honest, it's not my favorite pattern. I think it's a little bit overcomplicated for what people mostly want to use it for, but given that it's kind of standard now across a lot of JavaScript, I figured I may as well follow the same pattern. Effectively, this boils down to creating an instance of my class motion observer, attaching any event callbacks for the desired event types, and then calling the observe member to start listening, and then calling disconnect when you're done and the events are no longer needed. And honestly, for this type of API, I feel like it actually kind of justifies the observer pattern, as for the use cases that you're going to have for this library, it ends up allowing you to listen to motion events with very little code boilerplate. Unlike my usual projects where I rely on TypeScript private properties, which only work on a type level, I decided to use true JavaScript private properties for the internal values in the observer, since it was going to be a public library. JavaScript private properties, unlike TypeScript, actually enforce privacy at runtime and are unreflectable, meaning that I wouldn't have to worry about nosy devs manipulating internal state they didn't understand and breaking the system. This was definitely not motivated by me doing exactly that to other people's code in the past. Once that was done though, I wrote a really in-depth README documenting the library's capabilities and limitations and published it to NPM and GitHub for public use. In the 48 hours since then, it's gotten 90 downloads on the platform, which is honestly a lot more than I expected. Seriously, like, who are these people? The project is already seeing use in my game project I mentioned at the beginning of this video to create minigames with novel control methods. Currently, there are 3 using the APIs: a first-person shooter game where you tilt the device to aim your gun, a balancing game where you shift the device left and right to keep a beaker from falling down, and a glow stick priming minigame where you shake the device up and down to light a glow stick. I suspect we'll be making heavy use of this library for future minigames in the project. It's too early to say whether or not the library will be used by others, but I personally believe that it represents the best of its kind in standardizing and exposing device motion events to JavaScript, and so I very much hope it'll get wider use. That said, it's not without its limitations, largely due to the underlying sensor's precision. When testing gyroscope readings on the low-end Android device, they were conspicuously delayed by nearly a second, which made them infeasible for real-time play. This stuck out to me as odd, given that they were still coming in at full precision and at a reasonable interval, but just severely delayed. I've written this off as an outlier though, as this device was literally the cheapest phone that we could get on short notice due to my business partner's phone breaking in a foreign country in the middle of a networking conference. I've since watched close to a dozen other Android users test our application, and I've not seen the same delaying behavior on any of their more reasonably spec'd devices. One limitation I did encounter though was the constant drifting of the gyroscope's coordinate frame. Over several minutes of continuous measurement, its perception of up seemed to skew severely. This isn't particularly notable for minigames like the shooting game where only the change in orientation is relevant to gameplay, but it is for something like the balance game where it's important to know when the device is truly vertical. In my testing, the acceleration including gravity property of the accelerometer events seemed to remain true even when the gyroscope drifted, which means it's likely a good candidate for sensor fusion to correct the drifting gyroscope vertical, although that's left as an area for future research. For our use case specifically, this could also be resolved by requiring the user to manually calibrate by pressing a button when their device is facing up before each minigame. I also found a lot of inconsistency in the quote-unquote absolute measurements the devices reported, which is why I only said that they were hypothetically in Earth's coordinate frame. In actuality, they were regularly 10 to 20 degrees off of true north, even if the phone was held in the exact same position when the application was stopped and started. This had nothing to do with my implementation, it was simply a limitation of the sensors. I also learned after completing the code portion of this project that iOS devices as a whole do not support absolute orientation events, and instead rely on their non-standard WebKit compass heading property to record the difference between the reported z-axis and the compass north. This could be used to convert the relative coordinate frames iOS returns to absolute measurements there as well, which is another area of experimentation I might explore in the future. Linear acceleration also turned out to be quite disappointing compared to what I was expecting. Initially, I wanted to use the accelerometer readings to create high-precision camera movements, where the motion of my device would be mirrored to a virtual camera in an environment. My initial experiments with the accelerometer were encouraging and consisted of simply rendering the raw values onto the screen to see if they reasonably represented the movements I was making with my device. On a cursory glance, they seemed accurate, but as I tried to derive meaningful data out of them, I was consistently unable to do so. No matter if I filtered the readings through a high-pass filter, a Kalman filter, both, or anything in between, I could never get accurate motion to be reflected in my demo. The view would either drift wildly as soon as it was opened, or if I filtered it appropriately, it would hardly move at all unless I made huge lunges with the device. I'd read that accelerometers were inaccurate and prone to drift, but I'd felt as though those concerns were overstated given how accurate the raw sensor readings seemed to be. Unfortunately, after a few weeks of iteration, I had to accept that I'd fallen prone to both confirmation bias and a hefty dose of wishful thinking. The values I'd been reading were accurate for sharp acceleration spikes, but they weren't accurate for smooth motion, as any slow adjustment in acceleration would just get drowned out by the already incredibly noisy measurements. Even if it were possible to completely remove this noise, the constant sensor drift from the accelerometers I tested made pulling any meaningful data from the sensor almost impossible. And even if you compensated for the drift by including a calibration pass, it seemed almost random whether the drift would follow the device's coordinate system or the world coordinate system when moving the phone around, making it infeasible to mathematically isolate. Eventually, I had to accept that detecting sharp motions such as shaking or chopping the device in a specific direction was the best I could accomplish with the phone sensors that were available to me. Despite the limitations, however, I'm very satisfied with how this project went. I was able to implement all the core goals I'd set out when scoping the project, and get significantly further into the implementation than I'd expected within the timeframe. I unearthed a lot of information about device sensors, which I've now documented in the form of this presentation, as well as an article I'm going to publish online that contains the same information. And most importantly, I was able to create and publish a functionally complete library, which allows for the creation of motion-based experiences across all devices, a resource which has not previously existed in a satisfactory way. As I mentioned at the beginning of this talk, I believe as we move forwards towards a more open era of computing that the web is going to become an increasingly important platform to have more experiences and applications built on. And I'm proud to be a part of that in the form of these contributions to the space. If you're interested in browsing the library code or trying my demos on your own devices, please feel free to use the links below to access them. Thank you for taking the time to watch this presentation. I hope I created something worth your viewership. Thank you.